I don't think I have a tutoring session loaded for week 10. So nobody pick your nose or anything like that. All right. Good afternoon. Welcome back, everybody. We are in week 10 for our quantitative methods course. So hopefully you guys have questions today. Maybe we can we can run through the assignment. We can work out some of the problems. And I think today we're talking a little bit more about regression and analysis of variance. So in previous weeks, when we only had two groups and we were determining using inferential statistics to determine if there was statistical significance between groups, we were using t-tests. And if you recall, there were three types of t-tests: a one sample t-test, an independent t-test, and a dependent t-test. So this week, we're going to get into, well, what happens if you have three or more groups? Well, we could have 50 groups. And what if we want to determine if there's statistical significance? That's a mouthful. Statistical significance between one or more of those groups. Well, that's what we're going to get into today. So let me pause there. Let's have you guys jump into it. What questions do you have? Or are you just kind of sitting back and listening today?
Well, I have a few.
Please.
For question number 4, I know in the book, when he's walking you through how to do the steps on SPSS, it mentions a bootstrap feature, which I did not have on mine. So I wasn't sure how that would affect.
Oh, go see if you can still run the analysis. Yeah, I realize that there are versions of SPSS, and yes, maybe it's possible the basic version.
Yeah, so I did go ahead and run it and got my answers. However, I wasn't quite sure on that the y-intercept, how to, I guess, find that value using, I guess, that analysis. I don't know. I just wasn't looking at the right thing because I was able to get the other values. They were pointing right in front of me. So
yeah. Okay. So let's look at this. You probably got some kind of an analysis, and I could probably pull up the SPSS and run the analysis, but I've got this copy and pasted into my notes. So this is an example of your output. Does this look fairly familiar, Sarah, to what you were getting?
Yes.
So you run your analysis of variance. You're going to get you'll get your model summary up here, where it's going to talk to you. It'll give you your correlation analysis, okay? And then your coefficient of determination, that's R squared. Then you have your ANOVA report down here, and then your coefficients. Okay, you're going to need all of this to interpret and get these answers. Okay, so it's going to ask you about the correlation. It's going to ask you about the R squared value. And then over here, it's asking about the y-intercept. The y-intercept down here, that's our constant. It's B. Okay, this 84.873. That's our y-intercept. So y equals mx plus b. That's our slope formula. Okay. So at what point in this regression model does it intercept the y-intercept? Okay, so 84.84.
Okay, that's what I was thinking, because the B value is also represented as Y. The Y, okay. So I just want to make sure I was looking at that correctly.
And then when we're interpreting our analysis of variance, okay, so if you recall in weeks past when we were talking about like chi-squared statistic and t statistics, these analyses are, what we're doing is we're trying to figure out, is there statistical significance in this case? So we have we have a regression model, and what we're trying to say is, does this model predict, in this case, we're trying to predict album sales, okay, based on some independent variables, okay? So does for example, does advertising budget influence, does that lead to more album sales? And we would think so, yes. If we were working in marketing or advertising, we would think that there's a relationship between dollars spent on advertising and album sales in this case, that advertising is an independent variable that's predicting or leading to some sort of an outcome, in this case, album sales. So as we look at this ANOVA table, what this is telling us is that we could compare this F statistic with some sort of a critical value of F. Well, we don't need an F table to be able to do that, because we can look at this significance level. Remember, we've always talked about, we want a really high test statistic. So in this case, it's an F statistic and a really small p-value. And to interpret this in lay terms, is this significance value, and it's not literally 0.000, it's probably some very small value. If we took this out to 4, 5, 6 decimal points, we would eventually find what it's significant at. It might be 0.0001. Okay, but the point there is 0.0001, is that smaller than or less than 0.05? What's the answer? Yes, it is smaller. Therefore, we reject the null hypothesis. This this regression model is predictive of album sales, is what that's saying. It's statistically significant. We have a really high F value and a really small P value. Are there other questions on kind of interpreting this? And now that I actually looked at the problem, it's not advertising without album sales. We're actually using number of radio plays. That's our independent variable, or our predictor variable, and the outcome is album sales.
So then, continuing through the next problems, we would still use the number of plays for inputting that data.
Right. So what?
The formula.
So you're talking about number 6 when it asks us to actually write out the our regression formula.
Yeah, for 6 and 7.
So okay, so in this case, what it's saying is, based on this analysis here, okay, how do we write this formula? And it doesn't matter if you put the MX, the 3.939 before or after. Okay, all this is saying is that we're trying to predict album sales. That's our outcome variable. Okay, so album sales equals our constant, which is 84.87. That's our y-intercept, okay, plus 3.939, 3.93x. Okay, so in this case, what we're saying is, what is our independent variable? What were we measuring up here? What was our independent variable for number 4? What's predicting album sales?
The number of plays on the radio.
Number of airplays. So what this is saying is that we have a constant of 84.873, that's our y-intercept, that for every 1 airplay, we see an increase in this component of the formula of 3.939. So that's what we're doing for number 7. We're going to actually predict album sales. So what if we had 1,500 airplays? Based on this regression model, how many album sales would we see with 1,500 airplays? Well, replace X with 1,500. Well, it actually looks like first it's asking us for 150. So 150 airplays, replace that with X. So 3.939 times 150, you should get 590.85 plus our constant. So we would see 675.7 album sales with 150 airplays. Well, what about 1,500? You can check my math, but you should get approximately 5,993.4. Just replace X with your independent variable. And well, the number of independent variable. You know, in this case, we could have as many independent variables as we want. And we could have run this analysis with number of airplays, advertising dollars, you know, minutes of radio airplay. I don't know whatever. I mean, you pick the independent, you could have as many independent variables as you want in this formula. You could have 10, you could have 20. In this case, we just, for simplicity's sake, we just had 1. Well, what if we had 2? We could have had, you know, advertising dollars and number of airplays. In that case, our formula, though it would have looked a little bit more complex, constant might have changed a little bit, but let's say, for example, it was 84.873 plus your first independent variable. This value is a change in that independent variable at 3.939 plus the change in the second independent variable. So maybe it was 3.2 Y or X or whatever. Whatever that second independent variable was. For the sake of simplicity, like I said, for this week, for this question, we were just using 1 independent variable, but we'll get into example problems where you'll have multiple independent or predictor variables, multiple independent variables. Does that make sense, Sarah? Is that answering your question? Brian, is that kind of helpful to walk through?
Is there a different formula if you have, if you're looking at more variables?
No.
Okay, it'd be the same.
All a regression model is doing is it's looking at, is there a relation? It looks at the relationship between the it's a predictor model. Oh. You know, and in real world application, there is great use for this. What if we said, all right, let's say that you're a golf club manufacturer and you want to know how many times can a particular golf club hit a golf ball before it becomes defective. All right, it starts to wear down. Golf companies, tennis racket maker, companies, shoe manufacturers, they're all interested in how long their product will last. They run those products through trials and trials and trials and trials. How, I'm looking up at a light bulb. How many times can I flip the switch on this light bulb? How long can it stay on before it burns out? Companies test their products over and over and over again, and they create prediction models in order to determine and estimate, if you will, how long a light bulb will last, how many times can a golf club hit a ball before it starts to become defective, or a tennis racket, or how many times can you hit a tennis ball, play with a particular tennis racket before it needs restrung? Companies want to know those things. So in this case, we're talking about a business example, and we could have infinite number of variables. that predict album sales. The more independent variables that you have, and this is in general, the stronger your prediction model, right? So if we had 10 variables that, predictor variables, it's going to be a stronger predictor of album sales, but maybe 10, sometimes having too many variables becomes overly complicated. We want the fewest number of variables that gives us the strongest prediction model. Just having more and more random variables doesn't necessarily make it a stronger model, because if we had 20 different variables, well, one, that's difficult to collect that much data. But would a model of 3 be almost just as helpful? Sometimes it is. Sometimes it is. But to directly answer your question, yes, there are plenty of models that have more independent variables, and we'll probably have some of those examples. I just wanted you to see what this looks like with one predictor variable. Brianna, is that, you kind of nodded earlier, is that helpful? Do you have questions on 4, 5, 6, or 7?
No, that helped me out a lot. I had like similar questions that she had, so.
Okay, good.
Thank you.
Good. So did you guys get a chance to, have you done number 8 yet? Have you looked at that? So number 8's asking us to rerun the regression analysis for album sales, but now use attractiveness of band as the predictor variable. So in this case, what they're saying is they gave people a survey and said, okay, how attractive is this group? On a scale, let's just say on a scale from 1 to 10. Which some research might take a look at. But anyway, so yeah, so they were going to use that as the predictor model. Have you guys had a chance to run that analysis? Okay.
Yes, my numbers are off somewhere. I'm wondering if I just plugged the variables into the wrong spots, but.
So
For the
I just
other
showed
one.
you. So let's say that we run the analysis. And so this question is asking us to rewrite our formula, write our regression formula. Let's say that we just ran the analysis, and this is what we come up with. We get our model summary, our ANOVA table, and our coefficients. Okay, SPSS in all its magic and brilliance spits this out in 0.5 seconds. All right. So let's break this down and write our model together. Okay, so for this question, how are we going to write this formula? What's our outcome variable? What are we trying to predict? What's our dependent variable for number 8?
Album sales?
It is. So it's still album sales. And so now instead of airplays as our independent variable, our predictor variable, what's our predictor variable? Not airplays, but what?
The attractiveness of the band.
Attractiveness of the band. Okay. So assuming that we get this output, how would we write our formula? It's going to be album sales equals what? What's our y-intercept going to be?
That's 65.51.
Yep, 65.51. So album sales equals 65.51 plus some change in our independent variable. Some change in our independent variable. So what is that?
Be the 18.861.
Yep, 18.861x. So for every change in attractiveness of the band from 1, 2, 3, 4, there is 18.861. Multiply that by x. So Yes, that should look like this. Album sales equals our y-intercept plus the change in our independent variable, 18.861x. And again, it doesn't matter how you order this, it's all the same. You know, you could have 18.861x plus 65.51, doesn't really matter. And we could then rerun this analysis, though I don't think you're asked on this assignment, you know, because we were just talking about having multiple predictor variables. I could ask you to rerun that analysis and use both independent variables together. Hopefully that helps to walk through those. And there's lots of examples in the book. You know, I really encourage you guys as you read through the textbook, and I'm pretty sure that I gave you the link for the companion website, or it's probably in the book as well, but you can go, Fields has a companion website, a supplemental website that you can go to completely free, where you can download his data files and practice with the problems that he's working as well in the book. So, so that's kind of our introduction to regression. Part 2 of the assignment, it's comparing several means. So this is where we're going to start getting into analysis of variance. So as I mentioned earlier, if you recall from previous weeks, like let's say we just had 2 universities. You know, in this case, what we have is NFL Combine data, a made-up data set. But one of the exercises they do at the NFL Combine is pretty standard. They put 225 pounds, you know, on the bench press, and they max rep, you know, find out how many times these athletes can bench press 225 pounds. So here's some made up data. Well, in weeks past, when we were doing t-tests, we could have only compared, for example, Ivy University with Southern University. Well, when we have multiple, you know, in this case, 3 or more groups, you know, sometimes students will say, well, why couldn't I just run multiple t-tests? Couldn't I just run a t-test and determine if there's a difference between Ivy and Southern, and then Southern and University of the North, and then run a third t-test with Ivy University and University of the North? In statistics, you're more likely to run into some kind of an error estimate when we run multiple t-tests like that. The more accurate, the more valid, the more appropriate way to run that analysis is, first of all, with what we're going to call an analysis of variance. So it's going to allow us to compare several groups at one time. We might not know which group is different from the other, and that's why we run what's called a post hoc analysis, and that will tell us which group is different from which. So this is our first introduction to analysis of variance. So for number 9, what it's going to ask you to do is get your descriptive statistics for these various universities. So that should be pretty straightforward. You know, point click, you know, it'll give you that information in SPSS. So run your analysis, get all the descriptive statistics, and then just fill in the blanks there. What I'd like us to spend some time on is looking at the analysis of variance. Okay. This is a relatively small data set. We realistically could calculate this out by hand, but that's no fun. SPSS will do this in half a second. So let's look at those results, and then let's break that down and interpret what that means. So SPSS is going to give you an ANOVA output. You know, it's basically going to have this information. It's going to give you sum of squares, your degrees of freedom, your mean square, and your F statistic. Now, if you knew nothing about analysis of variance, this should start looking still pretty familiar when we're talking about a test statistic and a p-value. I've kind of given you the life hack of statistics. What do we say? What do we, if we wanted to demonstrate significance between groups, do we want a small or large F statistic? If we're trying to say that there is significant difference between one or more of these groups, do we want a large F statistic or a small F statistic?
Large.
Large. And the opposite is true for our p-value. We want a small p-value. The smaller the p-value and the larger our test statistic, the more likely that there is statistical significance. Okay. Now, someone might say, well, 8.096, that's not that large. Well, it certainly is significant, and we don't need an F table to determine that significance level, because SPSS gives us the p value is 0.004 less than 0.05. Yes, it's much smaller. It is much smaller. So in this case, what we're saying is, what this is saying in lay terms is that one or more of these universities is statistically significant from the other, based on mean and variance within the groups, that there's some kind of a difference going on between the groups. Now, we don't know which is statistically significant from the other just yet, but we could run a post hoc analysis to be able to do that. And we can run our effect size. Okay, so in this case, when we determine that something is statistically significant or not significant, we can run our effect size, which tells us the magnitude of the effect, okay? The magnitude of difference, okay? So in this case, your formula for our effect size, SF stands for sum of squares, okay? So it's the sum of squares between groups, okay, divided by the sum of squares total. So this 163 sum of squares between groups divided by the sum of squares total. So 163 divided by 314 is 0.519. We take the square root of that, and that's 0.72. 0.72 is a medium effect size. Remember, it was like 0.2, 0.5, 0.8. So it's somewhere between a medium and a large effect, but 0.72, we quantify that as a medium effect size. Anytime that you run an analysis, it's always a good next step to try to calculate an effect size if you can. So, and this analysis asked us to do that. So if when you get to the final exam, if it asks you to run an analysis of variance and then interpret your results, if you're looking for max opportunity to earn points on that, write this down, run an effect size along with your analysis and integrate that into your interpretation, into your results.
How do we determine, I guess, are there different formulas for the effect size, I guess, based upon what numbers that we've run and come up with?
I'm sure there probably are. I am not, I don't have a master's or a doctorate in statistics. I try to read, field book fairly carefully, and from my experiences in stats class as well, this was the formula that I have used to calculate effect size for an analysis of variance.
Okay, for the ANOVA. Okay.
Yeah, for ANOVA,
Okay.
correct. That's right. So really, and then it asks us to interpret our findings. Really, to interpret our findings, we still need to go another step. We still need to figure out which group is different from the other. Okay, so we have all of our descriptive statistics here, and the ANOVA just told us that we reject the null hypothesis, that there seems to be statistical significance between one or more of these groups. Well, we still need to determine which group is different from the other. And in order to be able to do that, we need to run a post hoc analysis. Okay. And that's our Tukey HSD test. Okay. When you go into your ANOVA, into your settings, you can tell SPSS to give you the post hoc analyses. It will run that at the same time. I give you the formula here just so that you kind of see how that's done. It's our mean square within divided by the number. Okay, so back up here, when we get our output, our mean square within 10.067 divided by our number. So how many were in each group? 1, 2, 3, 4, 5, 6. So it's not 18 total. It's how many was in each group. Okay. So our mean square within 10.07 divided by 6. We take the square root of that. We should get 4.753. So in other words, what we're trying to calculate here is the difference between the means. So here we go back to our means, our average for each group. Okay, so you take the difference between the means. So what I'm doing down here, if you can kind of see my Excel work. All right, and I just wanted you to kind of see how this is done. You won't do this in Excel. SPSS will give you this output, but you're looking at the difference between the means. So what's the difference between 10.5 and 17.5? And that's 7, the difference between 10.5 and 12, and then the difference between 17.5 and 12. So so anything that is greater than 4.75, then there's going to be significant difference. So in other words, what this is saying is that there is a statistical difference between Ivy University and Southern. There is a statistical difference between Southern and University of the North, and there is not a statistical difference between Ivy University and University of the North. So when we write this up, okay, when we write up our analysis, they're going to cram a lot of information into an interpretation. So in this case, we say that ANOVA results suggested there was a significant difference between the mean number of bench press repetitions completed at 3 universities. Therein, we're going to report our ANOVA results, okay? We're going to get an F statistic. We report your degrees of freedom, 2 and 15. Let's go back to our output. Degrees of freedom between is 2, and within groups was 15. All right. So we report our degrees of freedom, and we report our F value. I know this is all highlighted already, but our 8.096. And actually, now that I'm looking at this, we should report our P value. Okay, this was, I'm reporting a p-value that what our alpha level is set at. I need to go back in and change this. So what was our p-value? 0.004. So a more accurate way to write this would have been p equals 0.004. I'll try to change that on my write-up. That's what's nice about SPSS and other statistical software programs. It's going to give you the exact p-value. If we were interpreting this, if we were, doing this analysis by hand, we would have needed to compare this F statistic with a critical value of F. And we would have, this is how we would have wrote it up, because we wouldn't have been able to calculate the exact p-value. We would have calculated our F statistic and compared that with an F table. But in this case, SPSS gives us the p-value. So report your p-value right there. It's always good in your interpretation to interpret your results in relation to the null hypothesis. Therefore, the null hypothesis that there was no significant difference between the three universities was rejected. We rejected the null hypothesis. All right. So that means that in lay terms, again, there is a significant difference between one or more of these universities. We've already looked at that, but now we need to say that in our analysis. Well, we do that through post hoc analysis, and we need to state what test we ran. We've already stated what test we ran to determine if there was differences. It was an ANOVA. Now we need to state what test we used for post hoc analysis, and that was our Tukey HSD test, all right, which determined that there was a significant difference between Southern University. And what's very helpful here is report your mean and your standard deviation for these groups, all right. So in this case, the mean for Southern, 17.5 plus or minus the standard deviation. So there was a significant difference between Southern University and the other two institutions. Remember, we noticed that down here, that there was a difference between Ivy and Southern, and then Southern and University of the North. So in this case, we're just, for simplicity's sake, we're just saying that there was statistical difference between Southern University and then the other two. Southern was significantly different from Ivy University, and Southern was significantly different from University of the North. All right. So in that one sentence, that tells us that Southern was different than the other two, but Ivy and University of the North were not significantly different. All right. You could deduce that from the way that this is written up. All right. And then we report our effect size. I see here in my write-up, somewhere in my notes, there was probably another way to calculate effect size. I give you the formula here for effect size of R squared. That way you can just calculate R. Anyway, so that's our interpretation. We state what test we ran, which was an ANOVA. If there was statistical significance, then we need to run our post hoc analysis. In this case, we ran a Tukey HSD test, and then we followed that all up with to determine magnitude of effect with effect size. And then it's always nice if you wrap up an interpretation with, generally speaking, what does this analysis suggest? Well, it suggests that on average, Southern University is outperforming both Ivy and University of the North, while those two schools are not significantly outperforming one another. So something along those lines. So there's a whole lot of information crammed into just a few sentences here. From what analysis did we run? What was the results of that analysis? It gives us some descriptive statistics with our mean and our standard deviation. We run an effect size, and we also interpret our results for the person reading. It's a mouthful. You guys wore out?
So we only do the post hoc analysis if we find a significant difference.
Yes. So
Okay.
if, and that's a good question. If we would have found, let's say that this would have been a really small F statistic, like 1.096, and then our p-value was, 0.07. 0.07 is not less than 0.05. But let's just say, for the sake of practice, you went ahead and did your post hoc analysis. All right. Well, if you would have done that with that small of an F statistic and that large of a p-value, what you would have found is that all of these differences would have been less than 4.75. Just like Ivy University and the University of the North, the difference between the means is 1.5. That's less than 4.75. So therefore, that suggests that those two schools are not significantly different from one another. If that F statistic would have been really small and the p-value were large, we would have seen all three of these difference values would have been less than the Tukey HSD result. So therefore, there'd be no reason to run a post hoc analysis just to then doubly confirm that there are no differences. So yes, if you find significance, then you need to follow up and determine which of your groups is different from one another. Because we could have 10 groups, we could have 100 groups, you could have an infinite number of groups in your analysis. All this ANOVA is doing is determining, is there, that is such a mouthful, statistical significance between one or more of these groups. It's the post hoc analysis that lets us determine which group is different from the other. That's the idea. And then just to bring it all together, always remember that anytime you run any kind of a statistical analysis and we're trying to determine, is there differences amongst groups or is the model predictive? If we get some kind of a test statistic, the larger the test statistic, the more likely there is significance. And on the other side, the smaller the p-value, the more likely there is significance. That wears me out walking through that. But yeah, 10 questions for this week. You guys have a leg up on anybody that wasn't here, but like I said, I just recorded this, so hopefully some others that didn't get to be here today can go back and watch this and walk through those problems. That's a crash course in regression and ANOVAs. Questions? Is your brain fried? You hanging in there, Sarah? Brianna, you hanging in there?
Getting in, yeah, getting there.
I'll try for tomorrow night's session. If people have questions about the homework, yes, we can jump into it. But I might try to come up with some additional example problems that we can work through. I certainly realize that repetition helps with all of this. So, and we've talked about it in weeks past in these sessions. If you just attend the tutoring sessions and just copy down the answers, yeah, you're going to get the points for the assignment, but you're going to really struggle when it comes time for the midterm and the final. We just finished up with a midterm. I have not had a chance to grade those just yet, but that is on the agenda for today, tomorrow, or Friday. Get through those and get you guys that feedback back. So, yeah. Thanks for being here.
Thank you, sir.
Good job, everybody. Any final questions before we wrap up?
Thank you, and I will try to log in tomorrow.
Yes, please. I think I saw your, I only briefly saw your email. Herman, are you on the road?
Yeah, we on the road
Okay.
and we're playing today, tomorrow, Friday, Saturday, and I think Sunday.
Wow.
Yeah, so it's just
That's
going
yeah, that's a lot of tennis over the next few days. So, well, enjoy the weather. Hopefully it's nice out wherever you guys are going. Good luck. Yeah. And yeah, hope everything's a raging success. Where are you guys?
We're going to Kentucky, sir.
Okay. All right. Good deal. Good deal.
Thank you.
All right. Well, drive safe. Yeah. And yeah, we'll see you when you get back, man.
Thank you.
Chris, and I think you had some people in and out of your office. Hopefully you were able to get something out of this as well.
Yeah, I'm good. Thank you. I really appreciate it.
All right. Absolutely. Absolutely. All right. Any final questions, Brianna or Sarah, before we wrap up? All right, guys. Thank you very much for being here. I'll see you guys. I'll see some of you tomorrow night, and we'll do a deeper dive into some of this stuff. All right.
All right,
See you later.
thank you.
Bye.
Bye.